Hey everyone, and welcome to this explainer. Have you ever stopped to actually think about how we control massive trillion-parameter artificial intelligence models? It's really tempting to just imagine these complex grids of data and mind-bending multidimensional matrices doing absolutely all the heavy lifting. But the truth? It's actually much more elegant than that. The simplest mathematical concept in existence, literally a single number, is the master control dial for every single neural network ever built. So today, we're going to strip away all that crazy complexity and look at the very atom of computation.
Okay, let's dive into this. A scalar is, quite simply, a number that stands alone. That's the key part. It stands alone. It carries magnitude and absolutely nothing else. There is no direction attached to it, no position in a list, no row or column index. It just is. And I really want to set the stage right here. Distinguishing a pure standalone number from a number that lives inside a larger structure is absolutely vital, because if you confuse the two, you don't just get a harmless math error, you get code that breaks in incredibly frustrating, silent ways.
Section 1. The dashboard analogy. Let's get a real feel for understanding scalars. To really build our intuition here, I want you to imagine you're sitting in the driver's seat of a car, staring at the dashboard. Think about your engine's thermometer reading, say 92 degrees Celsius. That reading is a pure scalar. It tells you one single, standalone fact, exactly how hot the engine is. It doesn't tell you the direction the heat is flowing, right? It's just a pure magnitude. Now think about your GPS coordinates. If I just say 40.7 degrees, by itself, that means nothing. Is that latitude? Is it longitude? It only makes sense as a structured, coordinated pair. That is a vector. But the scalar, it's just the thermometer. It has full meaning all on its own. It's funny, this distinction actually traces its roots way back to the 1840s. Physicists like Willard Gibbs and Oliver Heaviside were trying to map out things like electric fields and velocity. But before they formalized vector calculus, physicists were using the exact same mathematical notation for everything. And you can guess what happened. It led to these totally nonsensical category errors. Imagine trying to treat temperature like a vector. You'd literally be forced to ask a completely absurd question like, okay, in exactly which direction is 27 degrees? It's nonsense. Temperature doesn't have a direction. So the physics community officially adopted the Latin term scalus, which means relating to a scale, to cleanly define quantities that are pure magnitude.
Section 2. Scalars powering AI, the true engine of machine learning.
Fast forward to today, and that exact same 1840s logic runs our cutting-edge AI. Let's map this mathematical theory straight into everyday engineering reality. Now, what's really interesting about this slide is looking at these big 5ML components. We have the loss, a single scalar summarizing the entire error of your massive network. The learning rate, that's a scalar controlling exactly how massive your parameter updates are going to be. Then you have the temperature for probabilities, the attention scale that literally prevents your transformer models from exploding mathematically, and the gradient norm that decides when to clip those gradients. Every major architectural decision in deep learning relies on a single dial.
Let's actually look closely at just one of these, the softmax temperature. When a model predicts a probability, it takes raw scores, called logits, and passes them through a few mathematical steps. But notice the very first thing it does, dividing by the scalar t. That changes everything. If you set that temperature scalar really low, the resulting probability distribution becomes incredibly sharp and confident. If you set it high, the distribution flattens out, making the model much more exploratory. It's wild to think about, but a single scalar dictates the entire personality of the model's output.
So the crucial point is this. Without scalars, optimization algorithms fundamentally wouldn't work at all. Just think about it. If your loss function outputted a vector instead of a single scalar number, how on earth would the optimizer know which direction to minimize? You can't sort vectors. You need a single, unambiguous down direction. Scalars give us exactly that. They uniformly scale millions of dimensions simultaneously with just a single multiplication. For AI, they are absolutely non-negotiable.
Section 3. Inside memory, the engineering reality. We've talked a lot about the math, but let's look at how these are actually stored inside a computer's memory using a framework like PyTorch. You'd probably assume a single number takes virtually zero memory, right? Well, 100 bytes. That is the surprising, massive metadata overhead PyTorch attaches to just a single scalar tensor.
When you break it down, a standard Python float takes about 24 bytes, but a PyTorch tensor on the CPU, that takes around 120 bytes. Here's the crazy part. The actual float32 data itself only occupies 4 bytes. The rest is literally all metadata. Strides, sizes, device locations, and those heavy autograph graph connections.
The metadata is nearly 25 times larger than the data itself. It's an incredibly heavy piece of machinery for what is just a single atom of data.
Section 4. Code bugs that haunt you. Welcome to the danger phase.
Because tensors are handled in very specific ways by these frameworks, we hit a real danger zone. Picture two different tensors. First, you have a tensor with an empty bracket shape. That is a zero-dimensional scalar, pure magnitude. Then, you have a tensor with a shape of 1. That is a one-dimensional tensor. It's essentially a list that just happens to contain one item. It is a container. Now, they both print out the exact same single number on your screen, but confusing them? That will silently break your code. If you try to do distributed training or loss accumulation with a shape 1 tensor when PyTorch expects a pure scalar, your broadcasting behaves entirely differently, and your model just silently trains on garbage data.
But honestly, that's not even the scariest bug. This right here is the stuff of nightmares for machine learning engineers, the notorious missing dot item bug. A scalar tensor doesn't just hold the number, it holds a heavy reference to the entire massive computation graph that originally created it. If you add that tensor to a running total for your logging without calling dot item to extract just the pure Python float, you are keeping that entire graph in memory. Do that every step of a loop, and you will completely choke your GPU memory in a matter of minutes.
So how do we actually fix this? Here are your concrete engineering rules to live by. Number 1, always, and I mean always, use dot item when you are logging loss outside of the autograph graph. Number 2, use pure Python floats for non-differentiable things like your learning rates to avoid that 100-byte tensor overhead altogether. Number 3, if you do have a shape 1 tensor and you need a scalar, explicitly convert it using dot squeeze. And number 4, just remember that calling dot item forces the GPU and CPU to sync up, so definitely don't do it on every single iteration or you're going to severely throttle your training speed.
Section 5. The control panel. Let's build our mental model.
To wrap this all up, I want you to think of your neural network as a massive factory floor filled with millions or even billions of internal gears. You don't go in and touch those gears directly. Instead, you interact with a tiny centralized control panel of standalone dials. The loss dial tells you how badly the machine is running, and you're constantly trying to turn it to 0. The learning rate dial dictates the speed of your adjustments. The temperature dial tunes the sharpness of the outputs. The scale factor dial prevents the internal gears from jamming up. And this brilliantly illustrates our main point. Every single one of these master dials is a scalar. Which really leaves us with this final thought. A single scalar dial literally controls the fate of a billion parameters. So, go look at your training loops. Look closely at your loss accumulation. Are you entirely sure your code isn't confusing a pure dial with a list of 1? Go check your tensor shapes today. You might just find the exact bug that's been haunting you all along.